Functional verification. How do we make sure that the design works as per the specification? Usually what we do is we write Testbench. The Testbench will generate stimulus. The stimulus will be driven to the DUV. DUV is nothing but design under verification. People call this as DUT also. When the DUV produces output, all the output values will be collected by the Testbench, and then finally the Testbench is going to compare the output values with expected values. This is how the simulation is going to happen. But in reality, we focus more on finding bugs during simulation. So the most important question is, how are we going to find bugs, or how are we going to find more bugs? Or the most important question would be, how are we going to find bugs faster? That's where we look at new methodologies like constrained random coverage driven verification. If you look at traditionally, we do simulation with directed test cases, and the directed test cases have always been time consuming with respect to finding bugs. That's where we look at new languages like system verilog and methodologies like coverage driven verification. Also, during simulation, we need to spend more time on simulation debugging. Simulation debugging is the process which consumes 40 to 60% of the complete simulation cycle. This is where we need to think how to deal with verification. So we expect the verification engineers to be good at both design and test-bench programming. If we involve software programmers, obviously they would be able to write the test bench comfortably using object-oriented programming, something very similar to software program, but they might not be able to contribute enough for the simulation debugging. That's where we try to train electronics engineers like you on test bench programming. So if you are going to be good at both design fundamentals and test bench programming, it will be like killer combination for verification. It will be good. You think of simulation debugging. During simulation, the simulation stops because there is a data mismatch. Then you look at the waveform. Okay, here, this is the place where the data mismatch happens. Then you might need to identify the cause. That's the most important thing. What is the cause? If the design is SOC, then you need to identify a particular IP. Then within IP, you need to identify which particular module is creating the issue. It could be FSM, it could be FIFO, or it could be decoder. So what is the cause? How are you going to identify exactly which module is creating the issue? That's called simulation debugging process. And here the most important thing is how you are going to communicate the design issues to the designer. Once you identify, yes, this is the particular FSM, it gets into a deadlock condition. That's why I'm getting data mismatch at the system level, right? So once you identify the exact design issue, then you should be able to communicate the design issue to the designer. So here the most important thing is, how are you going to convince the designer, hey, this is the issue, then I want you to look at how it can be fixed. For example, if it is going to be issue with a particular finite state machine, then you might want to explain the designer, okay, fine, let's go for a whiteboard discussion. This is the particular FSM you have implemented, and this is the RTL coding style. There is some kind of issue because I know a little bit of RTL coding. So the more you communicate to the designer, you would be able to accept the design issue, and that's how the simulation debugging is going to happen. So simulation debugging is the critical thing. That's why we always prefer electronics engineers who are good at both test bench programming and digital design. All right. We discussed about simulation process, but we don't want to consider functional verification something like, to run simulation, we need to write test bench. Yes, we have written self-checking test bench and everything is going to happen like automated process. The test bench will generate stimulus, it will collect the output, it will compare the output with the expected values, everything is going to happen, and this is called simulation, and functional verification is over. It doesn't happen like this. Here, the big question is, are we confident enough to release the design for synthesis? What about our confidence? Just by doing simulation, we might not be able to gain enough confidence. So to improve the confidence level, we have to do multiple things. That's where we try to apply verification methodologies, different kinds of methodologies. Even before running simulation, we try to verify the RTL code through linting. I'm going to explain these methodologies a little later. And before writing Testbench, we try to define all kinds of test scenarios as part of the verification plan. We want to be more methodical because that increases our confidence level. We don't want to write Testbench straight away, like, okay, this is the specification, this is the design, and I'm going to write Testbench. It doesn't happen like this. So we try to verify the design before simulation through linting, and we capture all the details as part of the verification plan. We implement Testbench. We try to generate different kinds of coverage values. Look at here, functional coverage and code coverage. And we also implement assertions. It's called assertion-based verification. We need to look at different things like data comparison and protocol validation. Usually we implement scoreboard for the data comparison, but when it comes to protocol validation, we prefer assertions. This is how we do multiple things like data integrity checking, protocol validation, and coverage-based verification. And we also write different kinds of random test cases to generate different kinds of test scenarios. So we do multiple things, and that gives us confidence during simulation. Yes, we have done multiple things. We fixed almost all kinds of bugs in the design. So during verification sign-off, we look at the coverage report. Also, we look at how many bugs we identified. If we have identified more bugs, obviously the quality of verification is more. That's how functional verification happens. So verification is a detailed process. We can't simply say functional verification is nothing but writing Testbench in system Verilog or Verilog. Verification is not only about writing Testbench, it's a detailed process. As part of this process, we do different kinds of things to verify the design functionality. Let's look at the verification process. So here, there is a person called project manager. He's the one who owns the entire verification process. And there are two teams, Testbench developers, they are senior verification folks, and test case writers, they are junior verification folks, and there may be multiple verification leads. And all these people, they report to project manager. And he's the one who is going to look at DUT specification and define verification plan. This verification plan will have all the details, the design features, test scenarios, coverage model, self-checking strategies. It's going to have all the details about the complete verification process, how the simulation is going to happen. And to define this plan, obviously, is going to involve the team leads and the senior verification folks. And the entire team is going to look at the DUT specification, and based on that, they are going to define verification plan. And finally, project manager is going to look at the coverage closure, whether the coverage meets its expectations. And once it meets the expectations, then it will sign off the verification process. Look at here. Both test case writers and Testbench developers, they are going to refer DUT specification and verification plan. Testbench developers take the verification plan and implement the Testbench. It's called reusable verification environment. In this case, they are going to look at the Testbench architecture, and based on the architecture, they are going to write the Testbench program. Also, they will instantiate the DUT as part of the Testbench, and then they try to verify whether the Testbench works properly. So they are responsible for finding all kinds of bugs in the Testbench or verification environment. And once the verification environment becomes stable, so what they are going to do is they are going to write some basic test cases, and then they are going to verify whether the test bench works properly, the data flow happens properly. Once the verification environment becomes stable, then they will inform the test case writers to write test cases and run simulation. So these test case writers, usually they are junior verification engineers, so they refer DUT specification. They also refer verification plan. In verification plan, they look at different kinds of test scenarios, and they also try to understand how they can verify the DUT features, how many features are there and how many test cases required. And based on that, they write different kinds of random test cases, and that's how they are going to run a regression simulation. So during regression testing, they will run all the test cases one by one, or the test cases might happen in parallel. And from each test case, coverage will be generated, and finally all the coverages will be merged together, and the project manager is the one who is going to look at the merged coverage report, and if the coverage meets his expectation, then he would sign off the verification. So project manager is the one who is going to approve the design for synthesis. Then finally the design goes through synthesis, and then during synthesis process, the RTL code will be converted into gate level netlist. Now I want you to understand how we create verification plan. Let's look at the planning process. Verification plan. It's a detailed document. It will have all the details like DUT features. For example, if the DUT is going to be subsystem or system, then we need to look at how many IPs are there, and for each IP we need to identify the features, how many features are there for each IP, and how are we going to verify each and every component within system or subsystem. Then the other important thing is test bench architecture. How are we going to implement the test bench? How many test bench components we are planning to reuse, maybe from the previous version of the project, or how many verification IPs are there. Verification IPs are the components which we can buy from the vendors directly, especially for the standard protocols. Are we going to buy the verification IPs from third-party vendors, or are we going to create everything from the scratch? Based on the strategy, we are going to define test bench architecture. So basically, test bench architecture will have all the details of the test bench, like how many generators, how many drivers, how many monitors, what kind of scoreboards, from where we are going to collect the data, and how we are going to compare all the packets. And then how are we going to connect the coverage model with the scoreboard? Are we going to use mailbox, or are we going to use callbacks? That's what the architecture is going to define. And coverage model. It will have all the details of cover points and cover groups. So in system Verilog, basically we have the concept of functional coverage. So during simulation, we generate functional coverage, and we try to map the functional coverage with the DUT features. That's how we are going to track the simulation progress. So there may be questions like how much we have done in terms of simulation, how much more time is needed. During simulation, if your project manager is going to ask you like how much more time is needed for the verification sign off, then you should be able to say like 2 weeks more or 1 week more. How are you going to find based on functional coverage? And scoreboard, self-checking strategy. How are we going to collect the packets and compare the packets? And test scenarios. What kind of test scenarios we want to generate during simulation? How many test scenarios? Are there any unexpected scenarios? If we simulate the design with any unexpected scenario, how the design is going to react to such scenarios? We have to think of all these things. And then finally, we also make the verification plan as executable V plan. What it means is whatever the plan we defined on paper, we should be able to define the same plan on Word document or Excel sheet, and we should be able to feed this V plan to the simulator. Let's look at how it happens. So here, the test bench and the design that you have created, eventually they will be compiled, and it's going to be like compiled database on the simulator. That's how I want you to visualize this. The test bench and the design, everything has been compiled, and the whole thing is like compiled database. All the test cases have also been compiled, and we are going to run the test cases one by one during simulation. And this is V plan. For the DUT, it will have all the details based on the number of IPs or the number of subcomponents. So here there are 4 IPs. So we are going to look at, have we verified all the IPs? So we are going to run simulation. So initially, based on coverage, it's going to show the coverage value as 50%. So here IP1 has been covered, IP4 has been covered, and the remaining things are IP2 and IP3. That's why the coverage is 50%. So this is called executable V plan. We have defined the verification plan, and the simulator is generating the coverage value. During simulation, it back annotates the coverage value to the V plan. So what we have done is, we have defined the V plan, we have mapped the coverage points with each feature. We have done this, and this plan has been fed to the simulator. During simulation, the simulator back annotates the coverage value to the V plan, and this is how it's going to highlight the coverage value. Now, to cover the remaining IPs, we add more test cases. This time in the simulation, we are able to cover IP3, so the coverage improves up to 75%. Now, to cover IP2, we add some more test cases, and then finally we would be able to cover IP2, and eventually the coverage becomes 100%. And looking at this coverage closure, we are going to sign off the verification. That's how the simulation is going to happen. Here the important thing is, this verification plan is different from test plan. Most of the traditional engineers, they are familiar with test plan. That's why in the industry still people mix up the terms, like V plan and test plan, both are same. It's not actually same. They are totally different. When it comes to test plan, we think in terms of test cases. When it comes to verification plan, we think in terms of coverage, or I would say we think in terms of design features. Here you look at, we are not thinking in terms of test cases. We always look at the design features and then we run test cases, and here the design features will be verified in random sequence. It's not going to happen one by one. That's how coverage driven verification happens. This is called verification plan. But when it comes to test plan, what happens is, it's going to always happen one by one. We try to verify IP1, then IP2, then IP3, then IP4. That's called directed test case. So in test plan, what we do, for every IP, we identify the features. Let's say there are 50 features, then we try to write 50 different test cases. So for IP1, 50 test cases, for IP2, 50 test cases, for IP3, 25 test cases, for IP4, 30 test cases. Based on number of features, we write test cases. And then we try to run test cases one by one, one by one, one by one. Here the issue is, suppose if the bugs are lying in IP3, then it's going to take much time, because we are starting from IP1. IP1 itself takes a couple of weeks, and then we are done with IP1, then we move to IP2, but actually the bugs are lying in IP3. Then it's going to take much time. But when it comes to V plan, the simulation is going to happen randomly, and during random simulation, if we hit IP3, then we would be able to hit the bugs in IP3. That's how we would be able to find bugs faster. So there is a huge difference between verification plan and test plan, they are not same. When it comes to test plan, we think everything in terms of test cases, and for every design feature we write test case. But when it comes to verification plan, we think everything in terms of DUD features and coverage. All right. This is how the executable V plan would look like. You can make it hierarchical. You can also look at each IP, something like transmitter or processor, or you can also look at in terms of coverage. You can have different sections, and you would be able to map different kinds of coverage with the DUT features. You can map code coverage, you can map functional coverage, you can map assertion coverage, you can do all kinds of mappings. And it's up to you how you want to define the verification plan. You can make it like hierarchical. Okay, this is for a particular system on chip. Within system on chip, I have 10 different IPs, and for each IP, I have 10 different subcomponents, and for each subcomponent, these are all the features I'm targeting. So you can make it purely hierarchical, and then you can do the mapping, and during simulation, you can track how the coverage closure is going to happen. So the entire simulation is driven by coverage. That's why it's called coverage driven verification, not by test cases. So this is how the verification is going to happen. So if you are planning for coverage driven verification using system Verilog Testbench, this is how you need to approach.